In this question, we're given 5 different buffer solutions and asked to find pH. The easiest and fastest way to do this is to use the Henderson-Hasselbalch equation. I like to use this equation in this format, whether we're dealing with a weak acid or a weak base and its conjugate. The pH will always equal the pKa plus the log of the base concentration over the acid concentration. If you look at parts A, B, and C, we have a weak acid, acetic acid, and a salt that contains an ion common to that acid when it dissociates. That is, the acetate ion, which is the conjugate base of the weak acid. The one part that's really confusing, and I kind of wish they gave you this, is they didn't provide a Ka or a Kb value for you. So you're left to either look this up on your own or Google it. I'm going to give this to you right off the bat so that if that's the hang-up for you, you'll be able to just go on without having to watch the rest of the video. For acetic acid, the Ka value is 1.8 times 10 to the negative fifth. In parts D and E, we have a weak base, which is known as ethylamine, but the name isn't important, and a salt that has the conjugate acid of that weak base. C2H5NH3 is the conjugate acid of that weak base. Well, what they should give you in the problem, in my opinion, so that you're not left to hunt for this, either in Chapter 14, Table 14.2, or an appendix at the back of the book, or you could just Google the Kb values. This one is 5.5 times 10 to the negative fourth. Now that we have that out there, let's work through the problem in each of the 5 parts. In every single case, we'll use the Henderson-Hasselbalch equation, which involves the term pKa. Sometimes students get confused by that. The p of anything is the negative log of that thing. So pKa would be the negative log base 10 of the Ka value. So you can rewrite Henderson-Hasselbalch like this, where the pH is equal to the negative log of the Ka value plus the log of the base concentration over the acid concentration. The other piece to this, which I think is important, is identifying the acid and the base. In parts A, B, and C, we have acetic acid, the weak acid. Notice that they give you the term acid. That's a nice hint for us. That means the other substance will be the base. The acetate ion is the conjugate base of that acid. So these numbers are all the base numbers, and these numbers are all the acid numbers. And it's important to keep that straight when you plug into Henderson-Hasselbalch. For parts D and E, we're given a weak base. The first number listed is the base number, and the other concentrations are the conjugate acid of that base. So A, B, and C will be structured the same, similar to each other, but different than what you'll see for the structure of parts D and E. Okay, let's dive in. In part A, to find the pH, we'll take the negative log of the Ka value of acetic acid, 1.8 times 10 to the negative fifth, and we'll add the log of the ratio of concentrations of base over acid. And the base would be, in part A, 0.45, and the acid is 0.11. So So that would be log of 0.45 over 0.11. On your calculator, the negative log of the Ka value is 4.745, and the log of 0.45 over 0.11 is 0.612, and so that works out to be 5.36 for a pH. And we'll just follow this structure all the way through. In part B, it's the same acid, acetic acid. This time they switch our concentrations a little bit. They give us, for the base, 0.11, and for the acid, 0.45. So it's the inverse of what you had in part A. And this time it's negative 0.162. And that works out to be 3.863. Part C is going to look just like parts A and B. Except we'll plug in slightly different concentrations. In part C, they give us the exact same concentration for both the acid and the base, 0.47 for both of those. That means what you're taking the log of is a ratio that's equal to 1. Well, the log base 10 of 1 is 0. So in that case, the pH of the solution is the pKa of the weak acid. That'll be important when we get to titrations in the next couple of days. Part D. Now we have a weak base. We don't have the Ka value, but for any conjugate acid-base pair, we know that Ka times Kb is equal to Kw. So the Ka would be equal to the value of Kw over the Kb that they gave us, or they didn't give us, but we had to look up. And if you remember, Kw is always 1 times 10 to the negative 14th, and the Kb of this base is 5.5 times 10 to the negative 4th. So when you divide that out, it's 1.8 times 10 to the negative 11th. Now we have a Ka value, and we can use the Henderson-Hasselbalch equation as we had in parts A through C. So negative log of the Ka value is pKa, and this time we'll take the log of, just like before, base over acid concentrations, but this time the base concentration was the first number listed, and the acid concentration is the second number listed, because it's a base dissociation. So that works out to be 10.74 and 0.301. And if we add that together, it's 11.04 for the pH. Part E is going to look a lot like Part D. It's the same exact dissociation. And this time, if you look at Part E, the concentration of both the acid and the base are the same. In my case, the red numbers are 0.59 and 0.59. So when we take the log of that, we're taking the log of a ratio that's equal to 1. Well, the log base 10 of 1 is 0. So this time the pH is equal to the pKa, and once again when we take a look at titrations in the next couple of days, you'll see why that's an important instance.